Hey everybody, this is a video to help you get through the Castle prep for redox. No, not redox, that's coming up. So I got redox on the brain. This is Kinetics. No, I am not in the corner. You don't need to see me right now, but you do need to hear me. So let's hope you're not bumping. Also, I had to print this to PDF, so there might be some formatting issues. Like this might look a little different on your screen when you're taking it. It should be up here and up here, the other choices, but um, the understanding is what we're looking for, and the reason why right answers are right is what we're looking for. So let's get right into that. What is required for a chemical reaction to occur? Requirements is we're getting into collision theory. So I'm looking for someone that's going to talk to me about collision theory. Standard temperature and pressure. No, things can happen at other temperatures and pressures. The standard temperature and pressure has to do with me being able to get the same results in a different place. A catalyst. A catalyst is one way to speed up the reaction. It's not required. Equal numbers of moles of reactants and products. No, those things are never equal. Um, their number of moles are constant, not equal. The concentrations are constants. What I need is effective collisions between reactant particles. And effective means, remember, proper orientation in space and proper energy. And then, of course, the first piece that we don't overlook is that they actually, do have to collide. All right, number two, for a given chemical reaction, the addition of a catalyst provides a different pathway that, well, it doesn't increase. Oh, it does increase the reaction rate, doesn't it? It increases the reaction rate. Oh, where's this guy here? Do I have my eraser? Sorry, I've never recorded like this before, so I'm just looking to see. Huh. I'm better off doing it this way so I have my tools because I just want to erase that mark. So it does actually increase the reaction rate. So I can get rid of decreases the reaction rate. We know that when I add a catalyst, that's this. So I draw my XY axis, draw my curve, and then it is that dotted line under the curve that doesn't change the potential energy of the products or the potential energy of the reactant. So sorry, my dotted line's a little bad, but drawing with a mouse is hard. It does increase the reaction rate because what it does is it lowers this activation rate. So it was here, and now to the top of the dotted line, it's only here. I'm going to make that bigger just so we're good because this is an important concept, so I'm going to take the time. Okay, so now if I draw the dotted lines like this, and this being the dotted line of the new activated complex, I would go from this as the activation energy to now this. And we can see that I've effectively lowered the activation energy by this much, right? I lowered it that much. So I increased the reaction rate and has a lower activation energy. That is the whole reason why the reaction rate goes faster, is that we have a lower activation energy. Okay, yeah, unfortunately, I might have to do like 10 problems and stop and do the next 10 problems because it's probably also going to take a lot longer now that I'm not on the smart board. So I apologize, but I do hope it helps you with your understanding. So given this big balanced equation, blah, 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 I skip all over that stuff. This reaction occurs more quickly when powdered iron is used. Powdered iron is used instead of a single piece of iron because powdered iron, boom, powdered iron. If I powder the iron, which of the six factors that affect the rate of reaction am I manipulating is basically what this question is saying. It says is more metallic than a single piece of iron. There's no way powdered is more metallic. That doesn't even make sense. Absorbs less energy in a single piece of iron. I don't know anything about that. Acts as a better catalyst. It's obviously not a catalyst if I just powder it. What I've done is I created greater surface area than a single piece of iron. I've made it so the insides are now exposed to whatever it's reacting with. Number four, looks like it's going to be the same thing because it's talking about concentration. So each of the 4 test tubes contains a different concentration at the same temperature. I'm only changing one thing, concentration. If a gram cube of zinc is added to each test tube, in which test tube is the reaction going to occur the fastest? That's what I want to know. So when you see cube of zinc, you might instantly want to powder the zinc, but this problem isn't giving you that. This problem is saying which of these numbered concentrations is going to react faster. And we know the stronger the concentration, the faster the reaction. So 1 molar right up here with this 1 molar HCl means it's way more concentrated than 0.1 molar, 0.01 molar, and 0.001 molar. And we learned a lot about molarity in acids and bases. So this is applying previous learning to new learning. 1 molar will go faster, more concentrated, more reaction. A reaction is most likely to occur when reactant particles collide with proper energy only. Oh, see, I'm starting to get into definition of collision theory and what we would say effective collision. I don't see effective collision here, but I want effective collision's definition. So proper energy only, no, we know it needs proper energy and alignment. Proper orientation, which means alignment, only, no. Neither, but neither won't work. I need both. Both proper energy and proper orientation is what I need. That is what collision theory says. So there, we're through 5. Let's see if I can get through 10, and then I'll make a new video for the other 10, just so it's not a 35-minute video. Given the equation of potential energy diagram, represents 10 kilojoules. What is the heat of the reaction? Okay, I see. So that's saying 10, 20, 30, 40, 50, 60, right? And I know that this is 10. And then 20, 30, 40 is this guy. And I know that it is products minus reactants. So it's 40 minus 10. Whoops, that's a 10. 40 minus 10 is 30. Let's look. That answer choice is there. Boom. There we go. Oh, I just realized now I don't actually get to click it because I'm not on the computer program to show you that it's right. That's really unfortunate, but I want to be able to draw, and I don't have my smartboard. So doing this from home has its negative drawbacks, you know. Which arrow represents the potential energy of the reactants? It always starts from reactants here to products here. So B is the potential energy of the reactants. It's a great chart for me to cut and paste out into other things, right? Potential energy of the products is over here. A is the activation energy in the forward direction to get me up to the activated complex. C would be the potential energy of the activated complex. D would be the potential energy of the products. And I just wanted to give that as a little review. It's been a while since we've been together in class. Oh, this is for the next page. We're going to miss it, but that's okay. 8, the potential energy diagram, blah, blah, blah. When a catalyst is added to the reaction, it will change the value of. Well, I know, and this is a bad curve, but I know that a catalyst will do this. And so that's going to lower anything touching this line. I see 2 touches that line, and I see 3 touches that line. These guys touch that upper line up here, where 1 doesn't touch it and 4 doesn't touch it. So the answer is 2 and 3. They're the ones touching that top line. Okay, let's move on to number 9. And I believe it says on the bottom, this is where the formatting issues. It says base your answer to the potential energy to the diagram in the chemical reaction. Okay, the forward reaction is best described as. So forward is going from left to right. I see I'm starting at a low energy and ending at a higher energy. So I'm actually absorbing energy. It's endothermic. So right here, when I see energy is released and energy is released, those are wrong. So A and C are wrong. I know that energy is absorbed because I see it starts low and goes high. Then it says, is it exo or endo? We know that exo is giving off energy and finishes low. So this has got to be endo. The opposite, energy is being absorbed. Definition of endothermic. Which interval represents heat of reaction? Heat of reaction is delta H, and we know that it makes this. It's the final potential energy minus the initial potential energy. So I'm just going to call it H for now. You could call it potential energy initial or final, but that is this number minus this number, which means which one has the arrows starting and stopping at just those 2 points. That's going to be F. Okay. And then this page, given the diagram representing a closed system at constant temperature, which statement describes this system's equilibrium? So notice, I remember us doing this yesterday in class a little bit online. Same chemical, just changing phases. Changing phases is physical. Okay. So which statement describes the equilibrium? The mass of the water liquid equals the mass. Equilibrium has nothing to do with mass. And this question has nothing to do with physical equilibrium versus chemical equilibrium. It looks now like it's actually looking for the definition of equilibrium hidden in there. So the volume of the water equals the volume of the gas. Well, that's not necessarily true. I could do the same thing if there was only this much liquid and I had all gas up here. So that doesn't change. The number of moles of liquid equals the number of moles. No. The rate of the evaporation equals the rate. So whenever I get into this word equilibrium, what is always the same is the rate. Whether it goes from this water molecule going from liquid up into gas, and then a different gas coming back down into liquid, this might be called physical equilibrium. But with all equilibriums, what's the same is the rate. And that's one of the key pieces that I was trying to tell you when we learned about what equilibrium is that the Regents is going to try to get you to say the concentrations are equal when we know the concentrations are constant. Since we did through 3 pages and there's only 5, I'm just going to keep going and make one video. And so sorry about your luck. Some solid KNO3 remains at the bottom of the stoppered flask. Which statement explains why the flask is at equilibrium? Well, okay, why are they at equilibrium? The rate of the dissolving is equal to the rate of the crystallization. Right off the bat, that's the right number. The rate of the dissolving is greater? No, the rates have to be equal. And then the concentrations are constant. Okay, the concentration is equal to the concentration. No, concentrations aren't equal, and they're not greater. The concentrations are constant, and the rates are equal. So that's what we need to remember when we're dealing with any equilibrium. 13, given the equation representing a closed system, which statement describes the system at equilibrium? Again, equilibrium. As soon as I see equilibrium, I know it's the rates. So it's not the volumes. It's the rates. So it's the rate of the forward reaction is going to equal the rate of the reverse reaction. And here, this one says they're equal, where this one says they are unequal. When he says they're unequal, that's not true. The rates are not unequal at equilibrium. The rates are equal. The concentrations are constant. What occurs when the concentration of H2 is increased? Okay, so here's a formatting issue. So what I'm going to do is I'm just going to rewrite this 2NH3 over here, because that's what we're used to seeing. Your product is always on this right side. So I want to just kind of do this first. Get rid of this. So you'll have to apologize. There's going to be formatting issues, as we all, when they say in the news that we all have to deal with tough things, like this is what we're dealing with, which is tough. This is unfortunate. All right, so let's do it. What occurs when the concentration of H2 is increased? So if I increase H2, this is AATT. I know I move away from what I add and towards what I take. Sorry about that. And I move towards what I take. So this is an add, so I need to move away. Ding, ding, ding. Need to move away from what I add, which means shift to the right. I added a reactant, and I shift to the right. And then once I do that, let me switch colors. I know everything on the right goes up, and then everything on the right then goes down. So the initial adding of H2 doesn't mean anything. I added it and I stopped. And then what happens as I go to equilibrium, it shifts to the right and it uses up more H2. That's how it's actually uh, described and taught to. So it says the equilibrium shifts to the left. That's wrong. We just realized it shifts to the right. So every time it shifts left, wrong. We know it shifts to the right. And then it wants to know about N2. We did the whole thing out. We see here N2 decreases. So we're going to say the concentration of N2 decreases, not increases. And now we've done both parts of the problem and gotten full credit for our multiple choice question. And I understand it's a lot of work, but that's just how these things go. Welcome to chemistry. Which two factors must be equal when a chemical reaction each equilibrium? Again, definition of equilibrium. When we talk about equal, we're talking about the rates of the forward and the rates of the backwards. And here they're trying to get you to say the concentration, number of reactant particles, the mass. No, the rate of the forward reaction is equal to the rate of the reverse reaction, and we need to have that memorized. All right, so here's another issue here. So I'm going to rewrite this again. It's the same equation, 2NH3 gas plus energy. I'm just going to put it up there and block this out. And notice, yeah, I haven't even read the question yet, so this could be unneeded, but I want to just make sure we have a formatting piece that we're used to. Okay. Which changes occur when the temperature of this system is decreased? So this is another AATT, except for now a decrease of energy is a take. And I know I move towards what I take. So now it's going to move to the right because I took heat. So the concentration. Oh, so this is all just results. It doesn't even ask me to show right. So I need to finish my problem like I normally do. If I shift to the right, everything on the right goes then up and everything on the left goes down. So I want to find that. And I see HN, HN, H, NH3, H, NH3. Okay, so I see what's going on. I see H's and N's. Do I have one where they both decrease? Here they both increase, so that can't be right. And then here one decreases and one increases. That can't be right because they're on the same side of the arrow. So they have to do the same thing. That's for sure. Whichever way you decide, it's got to happen the same way. All right, so now we're talking H2 on one side, NH3 on the other. So right off the bat, they can't be the same if they're on the opposite sides of the arrow. They have to be different. So it's telling me D is right. The concentration of H2 decreases. We got that here. The concentration of NH3 increases. We got that here. Proves that we were right. N is right. And notice, once on these Le Chatelier problems, once this stuff happens, everything on the reactant side reacts the same way. Everything on the product side reacts the same way. All right, given this system at equilibrium, which changes occur when O2 is added to the system? So O2 added. So here is O2 added. If I add or subtract, we're talking AATT again. I'm going to go ahead and write that. And if I'm adding, I'm dealing here. AATT, away from what I add. So if I go away from what I add, I shift left. Is it looking for that? Shift to the right, shift to the right, shift to the left, shift to the left. So I don't shift right. A and B are out because they say I shift to the right. When in reality, I want to shift to the left. So I'm good there. It's C or D. Might as well go ahead and finish like we normally would. If I shift to the right or left, everything on the left goes up. Everything on the right goes then down. And so equilibrium shifts to the left and the concentration of PCl3 increases. I have here PCl3 decreases. So C's not right. Equilibrium shifts to the left and PCl decreases. That's what I have for my arrows, and that's where we stand. Okay, one more page, and this video is donezo. And I have a little bit to tell you about the castle and how it works while we're distance learning, so you might want to stay tuned. All right, ammonia is produced, blah, blah, blah. This is the Haber process, a famous reaction that happens on these tests a lot. The formation of ammonia is favored by. In other words, How do I make more of this happen? Well, if I increase pressure, I'm going to go, I have 4 moles here and I have 2 moles here. And if I increase pressure, I go towards the 2 right off the bat. Increased pressure is the way to go. So that tells me decrease pressure is the opposite. If I decrease pressure, I go towards more moles. So that's wrong. Remove N2. If I take N2, I move towards what I take. That would make me go left. I don't want to do that. Remove H2, same thing. I would still moving a reactant, so I'd go left. So B, C, and D make you go left. I want to go right. This is a kind of a tricky question. You really have to know Le Chatelier's to be able to apply it. And I hope we're getting that strong. All right. The activation and the reverse reaction is represented by, well, we know that this is the activation energy in the forward reaction, which is B. And luckily, there's no just B here for you to make that mistake. Okay. We also know that the activation energy in the reverse reaction is here. So now we're saying which 2 letters make up this, and it's C is part of it, and B is the other part of it. So it's C and B. Notice D is not in there, and A has this piece that messes it up. So that's not going to be in there. So we need C and B to be our correct answer. And it says B and C. That works. B and C is the same as C and B. And as the temperature of a chemical reaction in a gas phase is increased, the rate of the reaction increases because of fewer particle collisions. That's the exact opposite. More effective particle collisions occur. Sounds good. Required activation energy increases. No. The concentration of the reactants increases. If I increase temperature, no, I have more effective collisions. They're going to collide more often and with more force. And with that, we've gone through all 20 questions so that you guys can see what's what. So before I let you go, I want 2 things. Ready? I want you to do the prep before you do the quiz. And I want you to make sure you do the prep before you take the test. So the test is now 50 questions. If you do the quiz or the test without doing the prep, you will be at a serious, serious disadvantage. Just because we are learning from home doesn't mean that we don't go through the paces and look at the reason why the right answer is right and understand what's what. And that only happens on this prep. That's where you're given 2 chances. It's not just 1 chance. You only get 1 chance on the quiz and one chance on the test. So do yourself a favor, do the prep, watch this video, and do well on all the other things. Okay? With that, we're done.